Hi, in this video we will be going through an example problem for uniform circular motion. Here is the problem. A 2.50 gram coin, one of these red or yellow coins in the animation, is turning on a turntable which rotates at a rate of 15.0 revolutions per minute. The coin is 10.0 centimeters away from the center of the disc. Your goal is to determine A, the period of the coin's revolution, B, the tangential speed of the coin, and C, the friction force exerted on the coin by the table. So let's go ahead and get started. Here is our problem again, and we'll start, as always, by drawing a physical diagram of the scenario. I'm going to draw a side view, so we have the turntable there, and I've chosen to draw one of the red coins, and the blue dashed line there is the axis of rotation, the point at which, about which the turntable and the coin are rotating. So let's annotate this with some things we know. We know the radius, how far away the coin is from the center, is 10.0 centimeters. We know the mass of the coin is 2.50 grams. And we know that the turntable rotates at a rate of 15 revolutions per minute. Cycles per time is the units on that, which means that this quantity is a frequency. The frequency is 15.0 full revolutions each minute. And now we're going to start by finding the period of the coin's revolution and the tangential speed of the coin. But we're not ready to do that yet, actually. We are first going to draw a force diagram for the coin. So there we go. We've got a dot representing the coin. I've enclosed this coin in a dashed circle so that we know it's our system. The forces here, we have a gravitational force downward on the coin by the earth. We have an upward normal force on the coin by the turntable. And we have a friction force, and that's the force pulling the coin in toward the center of the circle. And we know it's a friction force because if the friction were to disappear, the coin would just slide off of the table. So that friction force is preventing sliding and bringing the coin in toward the center of the circle. We also know that the upward normal force and the downward gravitational force are balanced because the coin is not accelerating in the vertical direction. Let's go ahead and write down those subscript definitions real quick so we don't forget what our subscripts mean. Next, we need to define our choice in sign conventions. The positive radial direction is always pointed toward the center of the circle. In the diagram that I've drawn, that points to the right. The tangential direction points in the direction that the coin is moving. And based on the animation on the previous slide, the coin at this instant is moving into the screen. So I'm going to draw an arrow pointing into the screen, and the way that we represent that is an X with a circle around it. And then the Z direction is the direction perpendicular to the plane defined by the circle. It's a horizontal circle, so Z is in our vertical direction pointing upwards. So there we go. There are our sign conventions. And now we're ready to start tackling the problem. We'll start by figuring out the period in this green box. The frequency is 15 revolutions per minute. And in order to find the period, we'll need to convert that into SI units, which is, for frequency, hertz, or revolutions per second. And so we need to convert the minutes to seconds, and we do that by saying 1 minute is equal to 60 seconds, so we multiply that by that conversion factor. And when we do that math, we find that the frequency is 0.250 revolutions per second, or 0.250 hertz. So there we go. There's the frequency in SI units, and now we're ready to find the period. Period is 1 over the frequency. Frequency and periods are inverses of each other. And so the period is 1 over 0.250 hertz, or once you use your calculator to figure that out, we find out that the period is 4.00 seconds. So there we go. There's part A. The period of the coin's revolution, 4.00 seconds. Part B, we want to find the tangential speed of the coin. We're going to do that in this yellow box here. We're going to start by finding average speed, which is distance traveled over time. And if we look at one full revolution, then the distance traveled is the circumference, and the time that it takes to do that is the period. It's a circle. We can compute the circumference of a circle using 2 pi r, and then period, the variable for that is capital T. So when we go ahead and plug in values now, the radius is 10 centimeters, or 0.100 meters, and the period we found earlier is 4.00 seconds. When we compute all of that out, we find that our average speed is 0.157 meters per second. Since we're moving in uniform circular motion here, the average speed and the instantaneous speed have the same value. So we can go ahead and get rid of the bar above the v, and we can just say that our instantaneous speed is 0.157 meters per second. So there we go, part A and part B. We have found the period, we have found the speed. Part C now is to find the strength of the friction force exerted on the coin by the turntable. So I'm going to go ahead and simplify things on our screen a bit now, clean it up, and move that time period and the speed to the top right corner, and we are ready to start computing forces. In order to compute strengths of forces, we're probably going to need to use that force diagram and some laws of physics. So the first thing to do is we're going to write a net force equation based on the motion. We know that this coin is accelerating. It's not getting faster or slower, but there is a change in the velocity vector's direction, and so there is an acceleration. So when we add up our forces in the radial direction, we should get mass times the acceleration in the radial direction. That's Newton's second law. We're also going to write a net force equation based on the force diagram. When I add up my forces in the positive radial direction, I see that there's that friction force, and there are no other forces in the radial direction. So for this example, the net force in the radial direction is just the friction force on the coin by the turntable. So now we have two equations for the net force, one based on motion and one based on the force diagram, and we can go ahead and put those two together. So the mass times the acceleration in the radial direction is equal to the friction force on the coin by the turntable. From here on out in this yellow box, the computation I'm going to do will be on the left, and in blue text on the right will be the explanation for what I'm doing. So the next step that I'm going to follow here is take this vector equation and write it as a scalar equation. To do that, we need to indicate direction. The acceleration points toward the center of the circle, which is our positive radial direction, and the friction force also points toward the center of the circle, which is also our positive radial direction. So both of those scalars get plus signs in front of them. And we can clean this up, make it look a bit nicer. Mass times positive A is just mass times A, and we don't need the plus in front of the friction force. So there we go. There's our scalar equation all cleaned up. The next thing we're going to do is use our equation for the acceleration in the radial direction. This is what we found out from our lab. And when we do that, we replace acceleration with the quantity speed squared divided by radius. So mass times speed squared over radius is equal to the friction force on the coin by the turntable. That mv squared over r term you may notice or recognize as our mathematical model for the net force in the radial direction. So there we go. What I'm going to do next real quick is just switch which thing is on the left and right side of the equal sign, because I want the unknown to be on the left side of the equal sign. That's not necessary, but I think it makes it look a little bit nicer. And now I say the friction is what I'm looking for, and on the right side of that equal sign are all things I know. I know the mass, I know the speed, I know the radius. So I can now plug in number values with units. In SI units, the mass of the coin is 0.00250 kilograms. Don't forget to convert that grams to kilograms. The speed we found earlier was 0.157 meters per second, and we're going to square that quantity, and then we're going to divide by the radius, which in SI units is 0.100 meters. Plugging all of that into the calculator, we find that the friction force is 0.000617 newtons. We don't expect a big friction force. It probably doesn't require much force to keep a very lightweight coin rotating on the turntable. And then the last step here is we have the strength of the friction force, but the question asks for the full friction force, which is a vector. So I'm going to put the vector arrow above the F and indicate the direction. So our full friction force vector on the coin by the turntable is 0.000617 newtons, and that friction force points toward the center of the circle. So this is the problem-solving approach for uniform circular motion, and these are the sorts of things I would expect to see when you're solving your own problems.